In this module, we're going to talk about what's called electronegativity and the polarity of a bond connecting two atoms together. All right, so first of all, a definition. What's electronegativity? This is how I think about it. It's the strength with which an element attracts electrons in a bond to another atom towards itself. Think of like a tug of war. Two atoms are attached to each other. They both want the electrons in that bond. They're pulling them towards themselves, but with different strengths. The stronger an element is, the greater its electronegativity. Now, these numbers are electronegativities based on what's called the Pauling scale. They don't have any units; they're dimensionless numbers. Notice a couple things. Fluorine is the most electronegative element in the periodic table. We don't show the noble gases over here because noble gases don't typically form bonds, and you have to have a bond to have electronegativity. Also the trend. The trend is that electronegativity increases up and to the right as you go up and right in the periodic table. Remember that. Memorize that electronegativity in general increases up and to the right. Also memorize the actual electronegativity of these elements. Hydrogen, 2.1. Lithium through fluorine. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. That's a real easy pattern because if you notice, if you start at 1 with lithium, it goes up by 0.5 every element you go up to until you reach fluorine, the most electronegative element in the periodic table, 4.0. And then fluorine through iodine, the halogens. And this is a little bit more forced, but the way I remember this is I remember 1, 2, 3. If you look at the difference, 4 to 3 is 1, then 3 to 2.8 is 0.2, and then 2.8 to 2.5 is 0.3. So memorize those. They will be very useful to you. Now, up here in this picture, this is showing 3 different compounds where the atoms either are the same or different. In hydrogen, the hydrogen molecule here, what this picture shows, this is called an electrostatic potential map, this picture. The red represents the electron density and the blue represents the lack of electron density, or high electron density red, low electron density blue. So here in the hydrogen molecule, because there's 2 hydrogen atoms, they both have the same electronegativity because they're the same element. They both pull on those electrons with the same strength, and so the electrons end up distributed evenly between the 2 atoms. In hydrogen fluoride, fluorine is more electronegative than hydrogen by quite a bit, 4.0 compared to 2.1. And so fluorine gets the greater electron density. Red also corresponds to a little bit of a negative charge, a partial negative charge, because more electrons, more negative charge. And blue corresponds to a little bit of a positive charge. Here, in sodium fluoride, fluorine's 4.0, sodium's 0.9. It's a really big difference in electronegativity. And so essentially the electrons are in the bond are pulled away from sodium and on fluorine. Not entirely, but almost all the way. So this difference in electronegativity between elements that are bonded to each other determines what kind of bond the atoms are attached to each other with. Now this isn't a bright line, this difference between the bond types. The bond types are covalent, polar covalent, and ionic. And it's like a sliding scale kind of. It's not like a hard line. I'm going to give you some numbers in a minute so that we can use those. But it's not just a bright line. For instance, we're going to call some compounds ionic, like sodium fluoride, but there's still some covalent character between those 2 atoms. In other words, there's a little bit of those electrons still kind of dangling over there by the sodium atom. So let's look at this. Here's those numbers I promised you. These are what we're going to use. If the difference in electronegativity is from 0 up to about 0.4, again, these aren't hard and fast, we call that bond a nonpolar covalent bond. In other words, there's not a big enough difference in electronegativity for the electrons to be shifted one way or the other, and so there's no real buildup of electron density on one side greater than the other. It's nonpolar. There aren't any poles. Now, if the difference in electronegativity is from about 0.5 to about 1.9, we're going to say that's a polar covalent bond. Covalent means that the electrons are still being shared between the two atoms, but polar means that there's a negative end and a positive end. The more electronegative element has the negative end of the pole, and the less electronegative element has the positive end. And now if the difference in electronegativity between the two atoms is about 2.0 or bigger, we're going to say, well, that's a big enough difference so that most of that electron density is on the more electronegative element, and we call that an ionic bond. So if we look at hydrogen fluoride, the difference in electronegativity is fluorine's 4.0 minus hydrogen's 2.1 is 1.9, and we would call this a polar covalent bond, although a very, very polar covalent bond. So what does that mean for it to be a polar covalent bond? It means that molecule, that bond, has what we call a dipole moment. This is one way of showing it, where you draw an arrow towards the more electronegative element with a little hatch on the end of the positive element. Or we can put these little partial charges here, partial negative on the fluorine, partial positive on the hydrogen. This is a lowercase Greek delta, and it means it's not a full-blown negative or positive charge, but just a part of one. And there's the electrostatic potential map for hydrogen fluoride. Red is negative, blue is positive. All right, so based on what we just said, can you tell me what kind of bond is predicted to be between beryllium and chlorine in beryllium chloride? So pause this for a second, figure it out, and then see if we agree. Right. So beryllium's electronegativity is 1.5, chlorine's is 3.0. So the difference in electronegativity is 3.0 minus 1.5 is 1.5, and that makes it a polar covalent bond.